Okay, so let's begin with the Joule-Thomson coefficient, and because this is related to the Joule-Thomson experiment, let me just very briefly remind you what we were doing there. So remember, there was a thermally insulated pipe and you pump some gas through the pipe, okay? In the specific experiment that Joule was doing, he was interested in the ideal gas. So the gas that was circulating in this pipe was very rarefied, but in our particular case we don't want that. In general, we want to study real gases, so any gas. Okay, so there is some flow of gas which has already become stationary, meaning that if I look to any intensive property anywhere in this tube, it will have a time independent value, okay? And in the experiment there was some porous object here, some piece of cotton wool in the case of Joule, that was somehow interrupting the flow, although it's porous so the gas can go through anyway. Thing is that there is going to be a gradient in pressure, okay? So if on the left hand side you have certain pressure P1, on the right hand side in principle you would have a lower pressure, okay? And this means that the temperature on the left hand side might be different from the temperature on the right hand side, okay? And in the case of an ideal gas, though, this is not the case. That was what Joule found. Joule found that T1 was equal to T2. And this is only for an ideal gas. However, if you have a real gas, in general, T1, it might be larger or smaller than than T2, but what we would like is that actually T1 is larger, let's say larger than T2, okay, or even much larger than T2, because in this fashion, with this kind of setup, we would then be able to cool down a gas just by simply making it expand or somehow interrupting the flow in some way, okay. And this is what is done to refrigerate gas, and in particular to refrigerate it so much that it will liquefy. Okay, so that's the whole point of this chapter really. And remember that we had said that such process in presence of thermally insulating walls was isenthalpic. So the enthalpy was a constant throughout, okay? So this means that the kind of object that I'm interested in this type of situation, let me just write it here, is the partial derivative of the temperature with respect to pressure at constant enthalpy, okay? So I'm interested to know how much does the temperature change if I change the pressure by interrupting the flow like this in an isenthalpic process. So this derivative here is something we can reduce with the tools that we learned in the previous lecture, because we have a partial derivative that involves two intensive variables but also an extensive variable. So everything we know can be applied here. And the first thing we would need to do to reduce this derivative, and remember, by reducing the derivative, I mean I want to express this thing in terms of readily available coefficients. For instance, alpha, the coefficient of thermal expansion, the isothermal compressibility, the heat capacity at constant pressure, and the thermodynamic variables themselves, okay? So let's try to do that. We know that the first step would be to try and get this potential to the numerator, okay? So how we do that? We can apply the cyclic property of the partial derivatives, and so that I would have here times the partial derivative with respect to pressure at constant, with respect to, what you see, that thing I wrote there, times the partial derivative of h with respect to temperature at constant pressure. Okay, and this is equal to -1. That's the identity. But from this identity, what we can write is that the partial derivative of t with respect to p at constant h is minus, and here in the numerator I can write the partial derivative of h with respect to p at constant t, that's this guy to the -1, and then in the denominator I just put this one, just like that, partial derivative of h with respect to t at constant p. So you see that both here in the numerator and in the denominator, the enthalpy appears in the upper part of the partial derivative, which is what we always want, okay? So once we have it in this shape, we can just replace partial derivative with respect of h within the corresponding fundamental thermodynamic relationship. Okay, so remember that dH equals TdS plus VdP. Okay, and here we divide, if you like, by dP, and the whole thing happens at constant temperature. And in the denominator we can write the same thing, TdS plus VdP, in this case divided by dt, and what remains constant here is the pressure. Okay, so what is this object equal to? Well, let's see. What we have is the minus, which we carry over, and then we have a partial derivative of the entropy with respect to pressure at constant temperature times temperature. So let me just write this properly. I will move this a little bit here. Okay, and then I put temperature there. Okay, and then here I have plus the pressure, and in the denominator what I have is the T times the partial derivative of S with respect to T at constant P. Now remember that this thing here is nothing but the reversibly absorbed heat divided by, or per unit temperature, in an isobaric process, or infinitesimal isobaric process. So this thing here is the heat capacity at constant pressure. Okay, so we can write that already, Cp. And here, well, we have one of those derivatives that are in principle complicated, but luckily we have Maxwell's relations. Okay, and in particular we have the Maxwell relation that says that this derivative there, the partial derivative of S with respect to P at constant T, equals, let me see, minus the partial derivative of B with respect to T at constant P. Okay, so let's put that here. So what we have is minus the partial derivative of V with respect to T at constant P. Well, there is a minus sign, and then there is also the T multiplying, and then there is the volume here. Okay, so what this equals in the end is 1 over the heat capacity at constant pressure. And then here I have, so remember that the coefficient of thermal expansion is 1 over B, partial derivative of B with respect to T at constant P, which is precisely what we have there. So actually what is written there is T alpha, well, TV alpha, and then, so this is because the minus goes with the minus sign, and then I have here minus the volume on the other side, so I could write the volume divided by Cp, and here I have T alpha minus 1. Okay, so this is the derivative that we were interested in. Okay, so this derivative, once again, the partial derivative of temperature with respect to pressure at constant enthalpy, which we are going to give a name. Okay, and this is, well, you would expect, the Joule-Thomson coefficient of the gas. Okay, alpha JT, and this is like this is just written there. Okay, V divided by Cp times T alpha minus 1. Okay, so the first thing that is striking from this expression is that you have T alpha minus 1. Okay, so it is absolutely clear that the quantity doesn't have a well-defined sign. Okay, so depending on what the temperature is and what other things are, you might have that alpha JT can be larger than 0, or alpha JT can be smaller than 0. Okay, and this has consequences because of what the coefficient means. Okay, so since the coefficient is the partial derivative of temperature with respect to pressure at constant enthalpy, if the coefficient is positive, it means that when I increase, when I decrease the pressure, say like this, on the two sides of the obstacle, let's say, because I have an expansion, then the temperature also goes down. Okay, and vice versa. If I increase the pressure, then the temperature goes up. Okay. However, if the coefficient is negative, I know that a decrease in pressure due to an expansion will result in a heating of the gas rather than cooling. Okay. So imagine this situation where you have a pipe with a gas in steady flow. It's well insulated, but it breaks. So there is a hole. And of course, the gas will expand to atmospheric pressure. This is high pressure gas flowing through the pipe, and outside there is atmospheric pressure, which can be much lower. And if you happen to be unlucky and you have a gas for which this coefficient is negative, the pipe will explode. Okay, because the temperature will raise very quickly, and if you have hydrogen there or something, well, you don't want that. So okay, so we have seen how to define the Joule-Thomson coefficient. As usual, I will write the name of it. That's the Joule-Thomson coefficient. And I have convinced you that the sign of this coefficient is important from the point of view of well, safety in general, but also of cooling the gas. Okay, so just so that you know, at normal pressures and temperatures that we normally operate with, most gases are in this situation. So the Joule-Thomson coefficient is positive. So it means that when you expand, they cool down. But there are some exceptions, like the hydrogen or the helium or the neon. Okay, in those cases you are in this dangerous situation. Okay, at just room temperature. Of course, if temperature is much lower, then you jump back into this region. Okay, so so then, before I move on with the next section, if you like to motivate the next section, let me just have a quick look where I will write it again. Alpha jt equals volume divided by Cp, and here we have T alpha minus 1. Okay, so we see that the sign is important, but what is the sign depending on? So this thing, okay, is going to be positive if and only if, and this seems clear if you look at the expression quickly, don't think too much about it, if T alpha is of course larger than 1. Okay, and this is what we want. However, this is just assuming that the heat capacity at constant pressure really is, for every gas and under any circumstances, positive, a positive number. Okay, because if this thing happens to be negative, well, then this condition here is flipped. Okay, so we really need to be sure that the heat capacity at constant pressure is always going to be positive. And well, you could believe that this is the case, or you could try to prove it. And this is what we're going to do in the next video. So using the principle of maximum entropy, we're going to see that for any stable thermodynamic system, this Cp is always larger than 0.